Hello, welcome to another interesting class in physics. My name is Wuzo Gift. Our topic today is Simple Harmonic Motion Part 2. Simple harmonic motion is simply a special type of periodic motion that has to do with the to and fro movement of objects along a straight line. Let's go on to see our objectives for this lesson. By the end of this class, you should be able to show the relationship between linear speed and angular speed. In our previous lesson, we were able to describe what simple harmonic motion is. We define some terms associated with simple harmonic motion, such as amplitude, frequency, and period. We also established the relationship between period, frequency, and angular velocity or speed. In this lesson, we'll be relating simple harmonic motion with uniform circular motion and also establish a relationship between linear speed and angular speed. From our previous lesson, we described periodic motion as any motion that repeats itself over a given period of time. Simple harmonic motion is only a type of periodic motion. That is to say, all simple harmonic motions are periodic motions, but not all periodic motions are simple harmonic motions. Periodic motions, such as the rotation of the Earth around the Sun and the movement of the hands of a clock, are not simple harmonic motions. This is because they move in one direction and do not have a restoring force. However, simple harmonic motion can be related to uniform circular motion. A uniform circular motion can be defined as the motion of an object around a circular path with constant speed. The one-dimensional projection of this motion can be described as simple harmonic motion. Now let's consider the motion of a ball attached to a uniformly rotating vertical turntable. This is the ball. If the shadow of this ball is projected on the floor, as shown here, it will be observed that while the ball is moving along the circular path, its shadow performs a simple harmonic motion, that is, moves to and fro along this path. Let's take, for instance, the ball starts rotating from this point. While it moves to this point, its shadow moves from this point to this point. And while the ball moves from this other point to this point, its shadow returns again to this other point. That means while the ball is performing a uniform circular motion, its shadow performs a simple harmonic motion, which is a to and fro motion. Let's also consider a particle P moving along a circular path. Let the projection of this P along the horizontal diameter be called Q. While particle P moves along the circumference of the circle, its projection Q moves to and fro from point F to point D and back to point F as long as the particle P keeps rotating. Therefore, while particle P is performing a uniform circular motion along the circumference, its projection Q performs a simple harmonic motion along the horizontal diameter. While particle P is at this point, its projection is at this point on the horizontal diameter. When particle P is at this point, its projection Q will be at this point on the horizontal diameter. And when particle P reaches this point, its projection Q will be at this point on the horizontal diameter. And when the particle P gets to this point, its projection will be at this point. Therefore, as the particle P undergoes a uniform circular motion, its projection Q undergoes a simple harmonic motion. Now let's consider this diagram. As particle P moves along the circular path, let A represent the radius of the circle and C the center of the circle. If S represents the arc length and X represents the distance of the projection of Q from the center, let's suppose the particle P moves from this point F. If theta represents the angle particle P makes with the horizontal diameter, it will be observed that while particle P moves along the circular path, the arc length also increases as well as the angle theta. So when particle P completes a revolution, that is, moves around the circle, the angle theta is equal to 360 degrees or 2 pi radians. As theta changes with time, the arc length S also changes with time. Now note that the length of an arc S is equal to the product of the radius of the circle and the angle in radians is subtends at the center of the circle. Mathematically, this implies that S is equal to arrow theta. When we make theta the subject, we have theta is equal to x over r. Now from our diagram, A represents the radius of the circle. Therefore, A is equal to r. Substituting A for r in this equation, we have theta is also equal to S over A. Now, as particle P moves along the circumference, the arc length S changes, giving us linear velocity, which is represented as change in displacement x over time, which can also be written as V equal to S over t. If we make S the subject of the formula, we have S is equal to V times t. More so, as the particle P moves along the circumference, the angular displacement theta also changes. Now, the rate of change of angular displacement gives us our angular velocity, omega, which is represented as omega equal to change in angular displacement over time. Mathematically, this is represented as omega equal to theta over t, where theta is the angular displacement. If we make theta the subject of the formula, we have theta is equal to omega t. But recall that we have theta to be equal to x over r. With this, we can deduce an equation that relates angular velocity with linear velocity. Now, before we proceed, bear these formulas in mind. Omega is equal to theta over t, V is equal to x over t, and theta is equal to x over r. Substituting x over r for theta in this equation, omega equal to theta over t, we have omega equal to s over r over t. By simplification, this is the same thing as omega equal to x over r times 1 over t. Since r times t is also the same thing as t times r, this equation can also be written as omega equal to x over t times 1 over r. Having done this, recall that v is equal to x over t. Therefore, substituting v for x over t here, we have omega is equal to v times 1 over r. This further gives us omega is equal to v over r. When we make v the subject of the formula, v is equal to r omega, or v equal to a omega. Remember that our radius from the diagram is represented with a. Having solved this, linear velocity can be related to angular velocity by the formula v equal to r omega, or v equal to a omega. Now let's take a quick comparison of linear velocity and angular velocity. First, linear velocity is given as the rate at which linear displacement changes with time. It is denoted by the symbol v. While angular velocity is the rate at which angular displacement changes with time, and it is denoted by the symbol omega. Next, linear velocity is measured in meters per second, while angular velocity is measured in radians per second. Mathematically, linear velocity is represented as v equal to x over t, while mathematically, angular velocity omega is represented as theta over t. Lastly, linear velocity relates with angular velocity by the formula v equal to a omega, where a is the amplitude or radius of the motion, while angular velocity relates with linear velocity by the formula omega equal to v over a, where a is the amplitude or radius of the motion. Now let's proceed to solve some examples. Example 1. The wheel of a lorry of radius 30 centimeters makes 10 revolutions per second. Calculate its angular and linear speed. Solution. From the question, we are given frequency to be 10 Hz, that is 10 revolutions per second, and our radius r is equal to 30 centimeters. Now we are asked to look for the angular speed and the linear speed. Let's take the angular speed first. What equation relates angular speed with frequency or radius? Of course, it is omega equal to 2 pi f. Substituting 10 for frequency in this formula, we have omega is equal to 2 times pi times 10. This gives us 20 pi radian per second. The next thing we have to solve for is linear speed. And linear speed is denoted by v. What formula relates linear speed with either frequency, radius, or angular velocity? the formula is V equal to R omega. So substituting 30 for our radius R and 20 pi for omega, we have V is equal to 30 times 20 pi. This gives us 600 pi centimeters per second. Now it's in centimeter because our radius was given in centimeter. Now let's take a look at another example. A car is traveling at a speed of 20 kilometers per hour on a freeway. If its tires have diameter 24 meters and are rolling without sliding or slipping, what is their angular velocity? Solution. From our question, we are given linear speed to be v equal to 20 km per hour. We can't just go ahead solving with 20 km per hour without first reducing it to meters per second because that's the unit of linear speed. So converting 20 km per hour, we have to convert the 20 kilometers to meters and then r to seconds. Note that 1,000 meters make 1 kilometer. Therefore, 20 kilometers is equal to 20 times 1,000. And also, 60 minutes make 1 hour and 60 seconds make 1 minute. Therefore, to convert 1 hour to seconds, we have 60 times 60. 20 times 1,000 gives us 20,000 and 60 times 60 gives us 3,600. When 20,000 is divided by 3,600, we have 5.6 meters per second. Another parameter that is given is diameter. And we know that diameter divided by 2 gives us our radius. That means 2 times radius gives us the diameter. So radius is equal to diameter over 2. Our diameter is 24 meters. Therefore, r is equal to 24 over 2, which is equal to 12 meters. Now recall that amplitude A is equal to the radius r and is also equal to 12 meters. We are asked to find angular velocity. What formula relates angular velocity with the parameter that are given, that is linear speed and radius? Of course, the formula is omega equal to v over a. Substituting 5.6 for linear velocity and 12 for amplitude a, we have omega is equal to 5.6 over 12. This gives us 0.5 radians per second. Now, before we go on to solve the last example for this class, I would like you to note the following about linear velocity in simple harmonic motion. In a simple harmonic motion, the linear velocity at any point is given by the formula v equal to omega square root of a square minus s square, where a is the amplitude of the motion and x is the displacement from equilibrium at any point in time. Now remember that amplitude is the maximum displacement of a body performing simple harmonic motion from equilibrium. Therefore, at maximum displacement, when s is equal to a, v is equal to omega square root of a square minus a square, since our s is equal to a at maximum displacement. A square minus a square gives us 0, and square root of 0 is equal to 0. Omega times 0 is equal to 0. So, at maximum displacement in a simple harmonic motion, linear velocity v is equal to 0. And also, at minimum displacement, when x is equal to 0, v is equal to omega times square root of a square minus 0 square, since our x is equal to 0. 0 square is equal to 0. A square minus 0 square is equal to a square. And square root of a square is a. Therefore, v is equal to omega a. From this, we can show that in a simple harmonic motion, velocity is minimum, that is equal to 0 at maximum displacement and maximum at minimum displacement. So let's look at the last example. Example 3. A particle is moving along a circular path. If the radius of the circle is 8 meters and the angular speed of the motion is 0.4 radians per second, find the velocity of the motion at A, maximum displacement, and B, minimum displacement. Solution. Since this is a simple harmonic motion, at maximum displacement, velocity is 0. Therefore, there is no need to solve. Now, the next thing is, we have to solve for the velocity at minimum displacement. And from our formula, at minimum displacement, v is equal to omega a. But from our question, omega is given as 0.4 radians per second, and A, which is also the radius, is given as 8 meters. Substituting these values into this formula, we have V is equal to 0.4 times 8, which is equal to 3.2 meters per second. Having solved that example, we have come to the end of this class. But before we go, let's take a quick summary of all we've done so far. First, we learned that all simple harmonic motions are periodic, but not all periodic motion are simple harmonic. We also defined circular motion as the motion of a body along a circular path with constant speed. Next, we learned that linear velocity can be expressed as the product of angular speed and the amplitude of the motion. Therefore, V is equal to A omega. And finally, we learned that in a simple harmonic motion, linear velocity is minimum at maximum displacement and maximum at minimum displacement. Now let's try out some test questions. Question 1. The relationship between angular velocity and linear velocity is given by dash. A, V is equal to omega over A. B, V is equal to A omega. C, V is equal to 2A omega. Or D, V is equal to 2 pi omega. The correct answer is option B, V equal to A omega. Now the last question. Suppose a boy turns his bicycle on his back and spins the gear wheel from rest until the wheel makes 90 revolutions per minute. Calculate the linear velocity if the radius of the wheel is 24 centimeters. The correct answer is option A, 72 pi centimeters per second. Thank you for your time. Till we meet again in another interesting physics class. Bye-bye.